So saying that, what do we realize? We realize that, oh, let's try to cut into 100 rectangles. Does that make things better? Of course. Let's try to cut into 1,000 rectangles. Do you think that will make the error less? Of course. What will make the error the least? The more the number of rectangles we cut into, the less the error. The more the number of rectangles, the less the error. That's what they started thinking of. So first, they built on what they know. They know areas of rectangles. So they said, you know what, how about we cut into rectangles and we try to approximate the area we're looking for by the area of those rectangles. And then they liked the idea because they saw it's a good approximation. But then they thought, you know what, how about we use more rectangles and more rectangles and more rectangles? Will that really help? Of course. The more rectangles you use, the less the error will be. I will show you an example from the book where they're using another function, but just to see how it becomes when you start first with 4 rectangles and then how it becomes when it becomes more rectangles. So first we will show you what happens when we have 10 rectangles. So let me show you. This is the curve they're working with. See, this is the approximation using 10 rectangles. It turned out to be 0.33. Then look, they used 20 rectangles. Do you see the error? The part that is above the curve and the part that is less, the part of the rectangles that is less than the curve and the part of the rectangles that are above, this is the error. But do you see how from 10 to 20 it became less? Then look what happens when we take 40 rectangles. I have to zoom in for you to see the error, right? Look what happens. As we come, look, if you take 10 rectangles, the approximated area will be 0.33. If you take 20 rectangles, it will be 0.3325. And you keep doing this. The more rectangles you get, the better approximation of the area that you will be able to calculate. This all gave them an idea how to make the rectangles grow bigger and bigger and bigger and bigger and bigger. They said, you know what? How about we study an approximation for n rectangles? N in general, not a certain number, 10, 20, 30, 40. But you know what we do in the end? After finding what the sum of the areas of n rectangles are, how about we make n go to infinity? This will be not only approximation of the area we're looking for, but this will be the answer for the area that we are looking for. This is basically what they thought about. You see the argument? Now what the question becomes is how to find R in general. So let's suppose I want to cut into n rectangles. Okay, cutting into 4 rectangles was fine. Cutting into 10 rectangles was tedious enough. How about cutting into n rectangles? What will happen? Let me show you how simple this is. See, once you have a methodology, things that are complicated become simpler. Look at this. You have the function y equals f of x equals x squared. You want to find the area between this function and the x-axis from x equals 0 to x equals 1. So over the interval from 0 to 1. So again, we're back to which graph? We're back to the graph from 0 to 1. We want the area under this graph. What I will do now, instead of cutting into just 4 rectangles or 10 rectangles or so on, I'm going to cut into n rectangles in general. What will happen when I cut into n rectangles in general? What will the width of each rectangle be? Well, the width of each rectangle will be the total width of all the interval from here to here, which is 1 minus 0 over how many rectangles are we cutting into? 1 over n. This is the width of every rectangle. Now, what are my endpoints. See, I'm working with the right endpoints. How do right endpoints look like? The first right endpoint will be 0 plus 1 width. So 1 over n. The second endpoint will be 0 plus 2 of those widths. So 2 over n. The third endpoint will be 0 plus 3 widths. So 3 over n. So what is the ith endpoint? The ith endpoint will be 0 plus I widths, which means I get what? I over n. Till when do I keep doing this? I keep doing this from 1, then 2, then 3, till I reach how many rectangles should I get? How many endpoints? How many right endpoints should I get? N right endpoints. So I do this from 1 to n. The right endpoints do not give me the heights. In order for me to calculate the areas of the rectangles, what do I want? I want the width of the rectangle, which is it's a constant. It's 1 over n. This is the width of every rectangle. Now, what do I want also to add the sums of the areas of the rectangles? I want the height of every rectangle. See, the height of the first rectangle uses the first right endpoint, which is 1 over n. So the height of the first rectangle will be f of 1 over n. The height of the second rectangle will be f of 2 over n. The height of the third rectangle will be f of 3 over n. This means that the height of the ith rectangle is f of I over n, which is the function evaluated at the ith endpoint. What do I have to do? I have to continue doing this till I reach the height of the nth rectangle. What's the height of nth rectangle? It's fn over n that we have, which is indeed what? It is 1. n over n is 1. يلي the end of where I want to stop. This is where I want to stop my calculations. So these are the heights. How to calculate the areas of those rectangles, which we call Rn, because we are taking n rectangles and adding their areas. What will the areas be? The areas will be the area of the first rectangle, which is the width times the height, plus width times height, plus width times height, plus till we reach the last one. So we will be, the width is common, so I will take it as a common factor, multiplied by the sum of all those heights. What is the representative of those heights? I over n. What is I starting from? 1. What is it ending with? N. Because I'm taking how many rectangles? N rectangles. See, this is now very easy to calculate. It's equal to 1 over n multiplied by the sum from 1 to n. What is f of I over n? F is the function that squares the input, so it becomes I squared over n squared. The only variable in this sum is I, not n. So that's why n squared is considered a constant here. We pull it outside, multiplied by 1 over n, we get 1 over n cubed. Times, what do I have left inside my summation? I have I squared. What's the summation of I squared from 1 to n? It's very simple. It's n plus 1, 2n plus 1 over 6. So how much is the full answer? The full answer is n plus 1, 2n plus 1 divided by 6n cubed. So when I cut into n rectangles, the areas of those rectangles will be equal to n plus 1, 2n plus 1 over 6n cubed. Try if it really works. Try n equal 4 to see if we get the same answer as we got before. Try n equals 10 to see if you get the same answer that we got before, and you will. And now what do? I want the number of rectangles to become very, 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 very large. So large. What's the largest thing we can take things into? We can take things into infinity. So the area that we will be looking for will be equal to the limit of this Rn as n blows out to infinity. So it is the limit. What did Rn turn out to be? n plus 1, 2n plus 1 over 6n cubed as n blows up to infinity. What will that help give me? n into n plus 1 to n plus 1 over 6n cubed at infinity. We know that at infinity, it's a power struggle. What's the highest power up? It's n times 2n. The highest power up is 2n cubed. What's the highest power down? 6n cubed. N cubed and n cubed, they cancel each other. We're left with 2 over 6, which when simplified, it's equal to 1 over 3. So when I have infinitely many rectangles, the error is 0. We have calculated the exact area that we are looking for. So I can say the exact area between the function f of x equals x squared and the x-axis over the interval from 0 to 1 is 1 over 3 square units. It's exact. So imagine this tool, this very important tool. It allows us to calculate areas between a curve and the x-axis. And if you look at what our knowledge was before this lesson, we only knew how to calculate areas of simple geometrical shapes like rectangles and squares and triangles and circles. We never knew how to calculate areas of things that are curved. Curves that we have, x squared and x cubed and so on, so like. That's why this is a very important tool. It's so huge to the extreme that it allowed us to calculate areas under any possible curve that you think of. All right, I'll be back.